our future in space as a country. How can you guys get engaged, contributing to SSA, both from an open source perspective, as well as from an engineering perspective as well, because I think it's a technical session, so we'll speak about engineering a lot more. And we'll also talk about the relevance of SSA, both in terms of, how it plays a role, with agencies like ISRO and NASA, with companies like SpaceX, or with military and defense applications as well. So I'll just go right ahead and maybe give you some background on why SSA is quite important. So as I mentioned earlier, a lot of us use space capabilities daily without even realizing that these capabilities are enabled by satellites. Now, the first satellite was launched in the 1950s. It was a Russian satellite. Again, it was just basically a test bed to see if we could go to space. Satellites inherently have been a very, they've been used for military applications early on. As we've evolved, and they've also been used now for civilian applications like climate change or climate tracking, weather prediction, Earth observation, banking, GPS, and all of those things that I mentioned earlier. Now, the population of satellites in the 1950s, like I said, was 1. In the 1960s, it was 7. 70s, it became 300. And today, we have about 15,000 satellite objects orbiting around the planet. Now, that is just the number of active satellites that orbit on the planet. Now, once satellites go up into orbit, there's no real way to bring them back down to the Earth. So once they become defunct or their mission life ends, they remain there forever. So that poses a very big problem at the moment, where you have limited amount of orbital slots. I hope all of you understand and know the different kinds of orbits that exist in space. So if you don't, let me just introduce them to you. You've got the low Earth orbit, which is LEO, which is from 0 to 2,000 kilometers altitude. This is mostly inhabited by satellites that track weather, by Elon Musk's Starlink constellation, and satellites that image the planet. Now, the distinct thing or feature about LEO satellites is that they orbit the planet 16 times a day, which means they have a very high revisit rate, and that's the reason they're used for those kinds of applications like imaging and these kinds of things. Now, moving ahead or above LEO from 2,000 to around 22,000 kilometers, you have, which is medium Earth orbit, or MEO in this case, and that orbital belt is populated mostly by satellites like telecommunication satellites, broadcasting systems, et cetera, that are focused on communication relays and enabling broadcasting services around the planet. Some of your broadcast services and broadband TV and all of these kinds of things come from MEO satellites. Now, finally, moving on to the final belt, like GEO satellites, geostationary orbit, that is at an altitude of 22,000 kilometers to about a limit of 35,000 kilometers. Now, the unique thing about geostationary satellites is that they're locked in with the rotation of the Earth, which means that they don't orbit around the planet. They focus on one location, and they're only focused on that particular location only, right? Because they're not really in orbit around the planet. They're locked in rotation with the Earth, kind of like how the moon is, locked in rotation with the Earth in some way. Now, given that we've established what the orbits are, LEO, MEO, and GEO, different kinds of satellites inhabit different kinds of orbits, as I mentioned earlier. And if we continue to flood or continue to take advantage of near-Earth orbit and continue to launch satellites without any regard for the orbital environment, there's only so much space up there. I mean, we understand that outer space is quite wide, and the distance between the Earth and Moon is quite vast, if you think about it. But satellites need enough space to be able to maintain their performance levels and not collide into one another, right? Now, collision then presents a problem because if I'm launching a satellite up into space with a limited amount of fuel and a limited amount of capability that is there, me or any satellite operator that is deviating from this mission profile will reduce their mission life on account of the fact that you're maneuvering away. So I'll come to all of these kinds of things much later. I just wanted to showcase and tell you that we have about multiple thousands of satellites planned. We've got increased mission costs, and we're only tracking 4% of the objects that are currently orbiting the planet. Now, this 4% number is significant because most of the objects that are being tracked are larger than 20 centimeters, but objects less than 20 centimeters also pose a massive threat because if that particular object is traveling at the speed of a bullet and it crashes into a satellite, the satellite stands no chance, really. Think of the object the size of a tennis ball coming and hitting something which is already fragile. And that means that your asset or satellite that costs about millions of dollars is now broken and it can be fixed. The analogy that I would like to provide for a collision-based scenario like this is, think about an accident that happens on the road. I'm sure, unfortunately, many of you have seen accidents. And what happens the next day is that the road is usually cleared. The accident and the debris that is on the road from the accident is cleared up. But in space, this is not possible because of the fact that it's extremely expensive, extremely dangerous, and there's no real way for us to, bring small fragments of debris down under. And that really is the difference between, sustainability or sustainable operations on a road versus sustainable operations in space. Let's just move on right now and go to a different use case. Right, like he said, I hope you were able to hear the audio or maybe even read the transcript, but that's from one of my favorite YouTubers. He is sailing from the coast of Mexico into India and just sailing through the Pacific and Atlantic Oceans all by himself. Now, the reason he's able to upload videos from the middle of the ocean really is because of the fact that he has access to Starlink. Now, Starlink has been quite a revolutionary, capability started by SpaceX, obviously, and we've gone from just maybe 32 or 50 Starlink satellites in 2018 to now having over 10,000 of them in orbit functioning. Right now, anything that goes into space is almost always going to be dual use, which means that it has a civilian purpose as well as a military purpose. Now, as you can see from the news reports that I'm showing on screen, during the Russia-Ukraine conflict, Russia tried to damage Ukraine's internet infrastructure as well as their power grids, etc., etc. But the US, in this case, allied with Ukraine and provided Starlink as a capability to ensure that communication could still happen during times of conflict. I don't know if you lot are aware, but Starlink right now has an office in Mumbai, and we're also trying to, or the Department of Telecom is currently in process of authorizing satellite-based communication technologies, in India. Moving on. So this is, just to give you a brief visualization, right, of what satellites look like inside of orbit. All of this, let me just use my laser pointer here. Yeah. So all of these dots that you see are individual pieces of objects. And whenever people see this image, whenever I go to conferences or give a presentation, everybody is just like, well, I didn't know so many satellites were up there, or we didn't know so many objects were out there. And that's really the point, because that's why we've, in-house, we've managed to, come up with a tool that can visualize each and every single object in orbit. Now, visualizing the problem is one half of it. Many of you play video games, or are avid fans of history in this case, and humanity as a whole has gone from conquering land to water to now air. Now, the way we navigate in these domains is by having a comprehensive understanding of what is going on in a particular domain. You can't travel without GPS. Air travel is not possible without air traffic control, without knowing where each and every single airplane is at any given moment in time. So why should space be any different? So visualizing each and every single thing that is up there in orbit, or inside of the space domain, is quite necessary towards enabling safe operations or safe navigation inside of space. Now, a lot of you must be wondering, what are these colors? What do these colors represent? The red that you see inside the image here is a piece of debris. It's not come down for a while. Green dots represent active satellites, like the Starlink that I mentioned earlier. Orange pieces are the final stages of debris. Now, most of you should be aware of the fact that Elon Musk's Falcon rockets always come back down to Earth. But the parts of the rocket that come back down to Earth are, they only travel up to 90 kilometers. They're only the first booster stage. A rocket has multiple stages. They've got the secondary stage as well as the final stage, which basically contains the satellite that are released into orbit. Now, these orange dots over here, they represent those final stages that never ever come back down. And it's only the booster stages that go up to around 90 kilometers that come back down. If you want to insert satellites into orbit, you have to go all the way up into 500 kilometers or 450 kilometers, or that sort of thing. Now, the white objects that we see are unknown objects. They need to be tracked a lot more, and I'll come to the current state of satellite tracking and maintaining such a catalog soon. Now, why do we need SSA, right? It's because of the fact that it has real-world implications. As we've established before, satellites play a vital role in many different facets of our lives, and one of those critical facets from a national perspective is that of the military, right? So in May 2025, during Opsendur, we detected a satellite making an unusual maneuver. 6 minutes before it crossed into that sensitive zone in the border areas, it adjusted its orbit, and we were able to determine that with that degree of accuracy. And this is what SSA enables, having an understanding of, what objects inhabit the domain, enables real-time detection of what's moving in space. And that can be used for collision avoidance, space traffic management, or even national security. So coming finally to the definition of, how do you define what SSA is, right? I'll just read it out to you. Space situational awareness is the comprehensive knowledge and understanding of the space environment, including tracking and characterizing all space objects, both natural and artificial, and monitoring space weather to ensure the safety, security, and sustainability of space activities. I'll keep it very simple. You need satellites for your daily life. Satellites are inherently dual use, and we have zero awareness. I mean, if you look up in the sky with your own eyes today, it's not really possible to understand what's going on up there. So we need specialized tools to understand what is going on in the space domain around the Earth's orbit. We have million-dollar assets that have real implications on our daily life. Any damage or disruption to these services means that our daily lives are impacted. And to mitigate this problem, we need SSA. Now, there are two types of SSA in this case, right? Or let me just come back to this slide, essentially. Now, to establish what is known as situational awareness, you would need to perform three crucial activities, right? First and foremost, just from a very intuitive, common sense perspective, awareness of a situation can be broken down into, three different facets. You perceive what your situation is, you understand what you perceive, and then you take an action that comes next, right? The same can be the same three rules: perception, comprehension, and projection, or taking of an action, can be applied to space situational awareness as well. Now, perception in the case of space situational awareness is understanding or gathering or tracking of satellites, right? Gathering data about these objects. If we want to track airplanes, for example, we use radars on the ground to make sure there's constant communication between the air traffic tower and the airplanes, so that we can map out their positions around the country. Right? Similar thing needs to happen for satellites as well. We need to have specialized sensors that can track satellites, and that is the way we perceive what these objects are in space. Now, once the data has been captured about these objects, there is a requirement for algorithms and a central data processing stack for us to be able to comprehend what this data means. And the image that you see over here is an actual image that is captured from one of the sensors. If I ask any one of you to tell me what this object is, you might just say, well, it just looks like a streak. I don't know what this object is, right? That's the reason why you need specialized algorithms to figure out what the stars, the dots that you see in the image are stars in the background, right? And with specialized algorithms, we're able to understand what these stars are, matching them with the star catalog, what the specialized object is in this case, which is the streak, and then understand what the object ID of this particular object is and where it is, moving in the sky and what its coordinates are. That's why you need specialized algorithms. You cannot just capture images and assume that you have situational awareness. Now, like I mentioned in the previous use case, if you see, or if you take a look at these types of analytics that we've performed, and what I mentioned earlier, that we were able to detect a maneuver. Now, this intelligence is quite vital for military operations, or to understand, let's say, if satellites are at risk of collision with one another. Once you gather the data, process the data, you're then able to analyze the data towards multiple different kinds of use cases. One of those use cases can be collision avoidance. The other one can be military, in the sense where we detect a military maneuver and then pass on that intelligence to the relevant stakeholders. Coming to again, some added context about why we need SSA. I mentioned to you earlier that we continue to launch satellites, and there is increased risk of collision. In fact, if you go to any open source website, like a spacetrack.org or celesttrack.org, I will mention these in the chat for later. You will be able to understand the severity of the collision events that we face every single day. ISRO, in fact, releases a collision report every year, and I urge many of you to go and read it. It will basically tell you that as the number of satellites increases in orbit, the risk of collision between two objects also increases. And if the risk of collision increases exponentially, we will have what's known as the Kessler syndrome. Now, the Kessler syndrome essentially is a scenario where there is a chain reaction of collisions that will continue to happen. One satellite collides with another, that generates about 3,000 pieces of debris. Now, these pieces of debris are in uncontrolled flight. They're moving in all different kinds of directions. They can hit another satellite, that starts another chain reaction, and the chain reaction continues until there is no way to use our orbit sustainably, right? So remember this definition for later. It's quite an interesting scenario, and what SSA is trying to do is to mitigate this risk. Many countries have adopted resolutions. I mentioned to you earlier that if satellites go up, they don't come down. But many countries, especially in the year of 2024 and 2025, they've adopted resolutions to ensure that once the satellite's time is up, maybe once it's spent 5 years in orbit and its mission life is over, it can generate a controlled re-entry burn into the Earth and crash into the oceans where it's all safe. Right? That means that dead satellites don't remain up in orbit, and we don't continue to pollute the orbits with debris. Now, as I mentioned to you, perception, comprehension, and projection, that essentially means that you need to generate data about space objects. You need algorithms that can process this data, and then you want to be able to analyze or take decisions based on this data that you want to go ahead with. Now, how do you gather this data? Okay, so like I mentioned earlier, there are specialized sensors that we need to use to be able to gather space object data. These sensors can be placed in space, and they can also be placed on the ground, right? This is a bit more technical, so I'll just come to what each of these things mean. Now, the easiest and most widespread way to capture imagery, all of you are familiar with telescopes that can capture objects. You've taken images with your phone of the moon, of the skies, and many of you, who've had the opportunity to go to Kasol or Uttarakhand or even the Himalayas or Leh Ladakh for that matter, know that the sky is very clear over there. Even with your phone cameras, you'll be able to see satellites whirring past, and unfortunately in major cities you can't see that. All of that technology is possible through optical systems. Your camera has lenses. Your camera has a semiconductor chip that processes or turns light into electronic signals that then turns it into an image. The same principle is being used over here in just a more specialized manner, to track satellites. So we have specialized telescopes that can track satellites from the ground. Now, we also have radars. Now, radars are powerful, mechanisms. Many of you have seen it in movies or on, where they've shown the radar blip to detect submarines on ships or missiles or, aircraft flying above and that sort of thing. Radars have a limited range. They can only track satellites up to 3,000 kilometers altitude, whereas telescopes, for that matter, can track to their theoretical limit, which is, in fact, infinity. The bigger the telescope is, the farther you're able to see, and that's really the principle. You also have passive RF systems. Now, passive RF systems are like listening devices. Think of them as sensors that can just listen to the communications that a satellite provides. Right? Many satellites that communicate with their ground stations through S and X frequency bands. Passive RF systems can listen or tap into these frequency bands to understand what the satellite is saying and when. In my line of business, we call satellite birds, and we use passive RF systems to hear the birds chirping. That's just some colloquial industry lingo. And then we also use lasers as well to track satellites. After this, if you have some time, please go and see the observatory in Hanle in Ladakh, which has a laser terminal that can point up into the sky and then track satellites that are moving with a very high degree of accuracy. So those are the four mechanisms through which satellites can be tracked, right? Now, let me before I come to what these data types mean, I'll just show you what an image actually looks like from a telescope. Now, this should be quite familiar to any of you who've been to Uttarakhand or Ladakh, where the skies are quite clear. You're able to see the stars in the background. So these dots that you see are stars. And because the camera is still and the satellites are orbiting against the motion of the Earth, faster than the motion of the Earth, they will appear as a streak because your camera is operating at a very high FPS, sometimes even sub 1 frame per second. So because of that, you're able to get these streaks, right? And from all of this, just from this image, our algorithms or SSA algorithms can tell you what this exact satellite object is, right? And I'll come to how we do that as well. The first thing that we do, right, when processing this image is all of this black space that you see is not necessary for us, right? I mean, it's just empty space. I'm not going to be able to get any useful information from it, so it doesn't matter. Now, I mean, a lot of you have probably used machine learning algorithms to kind of identify or label images, right? I mean, this is something that started way back in 2018 and 2019. The reason why AI is able to, detect images so quickly is because of the hard work of people that was done, many, many years ago. So if you take an image with your phone and you take an image of a bottle, the AI is able to tell that it's a bottle, right? So similar kind of algorithm is being used over here to detect what the intensity of the pixel is in the image. If the pixel is quite intense, which means that you see these white spots over here, then the algorithm will detect it as a feature. If the pixel is not very intense or the brightness is quite low, it's just going to skip it. It's not a relevant feature for us to be able to to go to the next step of image processing or processing of this particular data. Once we identify all of the features, we have algorithms that are able to determine, what these exact stars are. So I'll remove all of the other features. I'll only keep these white dots. I know where it is pointing at in the sky, because I know how the telescope is pointing up, right? At what location in the sky it's pointing. I'll get coordinates over here, X, Y, let's say in the celestial sky. And based on a star catalog that we've built internally, we're able to understand what this exact star is. Now, against the star catalog, you know what that particular star is. If I've identified what the star is, I know its location in the sky as well. Which means that if I know the location of the star here, what about the star here? I'll know that too. What about the star here? I'll know that too. What about these two stars here right next to the object? I'll know that as well. So because of this, I'm able to narrow down and understand where this object exactly is in the sky, right? And because we have prior information about, based on previous tracking data, I'm able to exactly predict that, okay, I knew that this particular object was going to come and fly over, let's say, Bangalore or Delhi for that matter, at this particular XYZ time. And here it is, my raw image data and the coordinate data that I'm able to process from this, we're able to sort of see that prediction was correct. Now, what kind of coordinate data is something that you might have a question about? So let's just go back to that slide. Now, before I go there, this is just, many of you will not be familiar, or if you're doing orbital mechanics in space, you will be familiar with what this image or diagram is, right? This round elliptical thing that you see is a satellite's orbit. A satellite's orbit is measured using different kinds of parameters. One of them is called perigee, which is the closest point in its orbit to the Earth. The other one is called apogee, which is the farthest point to the Earth. You also have the degree of inclination, which means how tilted is the satellite's orbit with respect to the planet. You also have angles of right ascension and declination. So I will not sit here and explain Keplerian orbital dynamics to you, but I just want you to understand or get a visualization of what is it that we're measuring. How is it that we're visualizing a satellite's orbit, and what kind of parameters are used or reference frames are used to kind of determine what the satellite's orbit is from this flat image that is here, right? So I mentioned that, this is just a 2D image from the telescope, right? How are we able to then determine what its, orbit is going to be from the 2D image? So I'll just come back to this image over here. Let's say, let's say our telescope is based on this location on the planet, and it's looking at this portion of the sky, right? And then this is our satellite. Excuse my bad diagrams, but here's the satellite. that is orbiting, and this is how it will translate to a 2D image. So you'll have one streak and multiple stars in the background, right? Um, that is what the image is that I showed you in the previous slide. I mean, it's just terribly drawn. Now, we need to then understand what this means in terms of, these orbital parameters. How do we translate this 2D image to these orbital parameters that I'm showing over here? A very simple way to visualize this is, let's draw a center circle on the ground. Okay. Now this is where your telescope is on the ground, let's say in Leh Ladakh. Right? And assume that this is the orbital sky. Right? So this is my telescope. It's pointing at this portion of the sky. It's taking that particular image. Now, in orbital dynamics, you will be able to understand, or if any of you are into astronomy, this is what's known as the celestial sky. Right? So the same streak that I'm showing you over here was captured by this particular telescope. Now, there are stars in the Milky Way. Imagine yourself standing here and looking up into the Milky Way galaxy. I'm just going to draw that over here, right? And we know what the position of the Milky Way galaxy is based on these two angles, omega and this one right here. These two angles over here are known as angles of right ascension and declination, or angles that can also be translated to azimuth and elevation, right? So my azimuth, so assume that this is a 360-degree circle on the ground. My azimuth will start, this is like 4 quadrants, imagine. So you have 90, 180, 270, and 360, right? So assume that, this is, let's say, a 45-degree angle, right? Now, imagine I detected a satellite here in the sky at a particular level of elevation. This angle here is what's known as my elevation, right? So these two angles is what is going to tell me or help me pinpoint this object in the sky, right? And that is in the celestial sky or celestial coordinate frame, it translates to these two things, first and foremost. With these parameters and using a combination of orbital dynamics that is incorporated into, let's say, data processing algorithms, we're able to determine the position of these objects. The first thing about satellite tracking or SSA is where is the satellite in the first place? If we're able to determine where the satellite is, what its position is, we're able to then predict where it's going to be 7 days from now. If we have a catalog, now I just gave you an example for one satellite, but we're doing this for around 40,000 of them. Now, if you know where 40,000 objects are in space at any given moment in time, you also know when they're going to pass over India. You know when they're going to come close to each other or collide with each other. You'll know what kind of images they're taking. If it's a military satellite, if it's a weather satellite as well, you'll know exactly how to support wildfire causes or communications, etc., etc., etc. The first and foremost step towards establishing space situational awareness is to perform satellite tracking for all 40,000 objects and then make a catalog of this data. You need a database, essentially, to start off with. That's your fundamental base layer. From your database, you can then go on towards analytics and these kinds of things. Now, what does the database contain, you might ask, right? So the database might contain raw data like this. It might contain range data, which is essentially giving you how high up or what kind of altitude the satellite has. It might give you its RF signature, what RF spectrum is it communicating in, right? And this can tell you a lot about a particular object. If I know, if I can combine this or fuse the angle information with the range information, I'll know exactly what orbit it is. If I can get the angle information and then predict it over a period of time, I'll know exactly what the size of the object is going to be. if we're keeping a close track or close tag on the object with the telescope, so let's say you're tracking a satellite with the telescope and then you track it as it moves across the sky for about 5 to 7 minutes, and you see the light intensity over here flickering, right? It might be like the intensity chart could be something like, going up and down, up and down, up and down, up and down like this. Or it could be something like, this as well. Now, if you're intuitive, you'll be able to understand that the satellites, which is the most reflective part of the satellite, the solar panels, right? Right, these things here. Now, if the intensity is really high, which means that the satellite is spinning at a much higher rate, which means the satellite is unstable. It's tumbling around in space. The intensity is flickering like a shining star would in orbit, and that is how we're able to determine if a satellite's tumbling in space, or if a satellite is getting ready to make a maneuver in space. It's all of these small data points that we can gather into the catalog that are then able to tell us how the satellite or object is behaving in orbit. Through position data, we can tell if it's moving from one place to the other. Through photocentric or photometric data, we're able to tell if the satellite's, what kind of position or what its attitude is. Is it is it pointing in this direction? Is it pointing in this direction? The difference in light intensity will tell us, what direction it's pointing in. If I know that it's pointing in this direction, I know it's imaging this area. If I know it's pointing in this direction, I know it's imaging this area. So my point being, different sensors can be used to gather different kinds of data points that can then fit into a database. Now, again, once it's inside of a database, it's a big data problem, right? How do you correlate different kinds of data points to take or bring out a story from it? And that is what is the point of space situational awareness. It's to accurately gather as much information as possible about the space domain. It's to then analyze this information and then utilize it for many different kinds of use cases: civilian use cases, military use cases, and or even unpredictable ones. Like, let's say tomorrow, if somebody or one of you wanted to launch a satellite in space, right, and you had made a student satellite, right? What would happen is, and I'm sure many of you have heard the fact that launches get delayed, or rocket launches get delayed by 5 minutes, by 2 hours, and these kinds of situations you probably heard in the media. But why, or one of the reasons why that actually happens is that if this is your rocket body and it's supposed to reach this point in space to release satellites, right? If one of your student satellites is in orbit over here, and let's say the control center in ISRO says that no, it's not very safe to launch because the rocket has to reach here, but at the time that it is launching and by the time it's getting to this point, there is another satellite that is in its way, in its trajectory over here, right? That is one of the use cases of SSA, because I know exactly when these satellites are going to be passing over this particular region. I can then launch the rocket in such a way that it is able to avoid collisions with their orbital path. So that's one of the ways we can analyze situations. Now, the next way is once the satellite gets released, it's like a baby bird flying in the sky. It doesn't know where it is. It's not connected to the ground station. You're nervous sitting in your control center in your control room, not knowing where your satellite is. Is it even switched on? What its position is? Is it going to collide with something else? That moves us on to the next stage where SSA helps you, right? Right from launch to satellite monitoring, right from to the satellite release as well. We're able to give you information or analytics about, okay, the satellite was released over here. Luckily, it's not in any collision path with any other object. And then you can and then we're able to then predict, okay, your ground station is over here. Satellite's going to come to this ground station at XYZ time. Be ready. Your satellite's coming over the ground station. Communicate and switch your satellite on. Right. So right from launch, early operations, routine operations, and to even deorbit, SSA is quite impactful and quite helpful in terms of helping orchestrate a space mission. This is just an example of what SSA data looks like, this is what's known as a two-line element, or TLE. And our two-line element set will contain information about the name of the satellite, the inclination, as I showed you earlier, the eccentricity of an orbit. So a highly eccentric orbit would mean something like this. A low eccentricity orbit would mean something more circular. Eccentricity is a function of how spherical an ellipse is, right? I mean, I'm sure if you guys have done engineering math, you'll know what the equation for an ellipse would be, right? There's a couple of other angles. So these are the angles that I told you, right? Extension of the ascending node, as well as the argument of perigee. These are a couple of angular information that is utilized when we, I mean, this is the input that is going into our analytics, is what I'm trying to say. This is the kind of data that is stored in the database that I'm talking about. All of these different data points will come together towards, the analysis that we need to do, right? And I'll just put some stuff into the chat so that you guys can also get started with it. Maybe after the session, I'll do that, where I'll share some links so that you guys can get started with, understanding what this input data is, how you can use this input data yourself sitting at home, and then predict, where a satellite is going to be. So if any of you have a telescope, or if any of you are heading over to Leh Ladakh anytime soon, you can, first and foremost, understand what this input data is, come up with your own Python script to understand the prediction or motion of a satellite, go to Leh Ladakh, and then, hey, I made a prediction that, from my coordinates on the ground, I was going to be able to see a satellite moving, right? And then let's just say, like, you have a telescope and you point it into the sky, and at the time that you predicted that the satellite would pass over you, it is actually passing over you. So it's quite easy to get started with space situational awareness. And it's not necessary that only SSA companies should be doing SSA, or only government bodies should be doing SSA. Students can get involved. A lot of universities around the world also have, observatories and SSA programs. If any of you are heading over to Pune, ISER Pune and Ayuka Pune have an observatory, please go visit it. They have a great SSA program as well. And you can just get started. If you're curious enough, you can just come up with your own script, take a telescope, point it at the sky, and then lo and behold, the satellite that you predicted was going to pass over you, over your head at that given duration in time, is actually passing overhead. So Europe has a very interesting model for SSA. We think that SSA data should be centralized to governments or SSA companies, but the way that Europe works, or ESA works, is that they have what's known as SmartNet, and they capture SSA data to fill into their catalog, not just from professional astronomers or professional companies or university telescopes, but also from amateur astronomers and students. So all of it, I mean, the more data we have, the better. It's not as if there needs to be a monopoly on SSA data, because the more data you have, the better space situational awareness you can provide. So that's what we need as a country, really. I'll just move on. Any questions until this point? I'm sorry, I've just been going on for about 50 minutes. Or maybe we'll keep questions to the end. You can note them down and I'll be able to answer them.
Yeah, we'll take the questions in the end. Okay, you can go on.
Sounds good. Sounds good. As I mentioned earlier, the reason we need an independent or indigenous, India-focused SSA catalog is because of two reasons. One is that the Russian space catalog of objects has maybe about 8,000 objects. And the US catalog might have about 25,000 objects. Now, there might be objects in the Russian catalog that are not there in the US catalog, and objects in the US catalog that are not there in the Russian catalog. So as a third-party neutral country who needs to operate in space, how do we understand where to trust or how to trust the data coming from anybody else? Because space operations are really, really difficult and they're really, really hard, right? If you were to make a financial decision tomorrow, you would gather all of the data points necessary before making that financial decision. right? How do you ensure that you have trust in your GPS systems or trust in your banking systems and all of these kinds of things, right? Space operations being critical, it's important to generate that trust, and that trust can only be generated if we have our own indigenous data sets or our own indigenous database of space objects, and if we're able to verify against a global standard, what if our database or the data that we're collecting is accurate. So it's quite important that we take from other catalogs, yes, take inspiration from them, but also start, pushing for these capabilities indigenously as well. So this is the US's space surveillance network. They have telescopes all over the world. They have radars, telescopes, satellites that are tracking, objects. China also has a few located in all of these countries that I'm mentioning to you. And using these sensor networks, both countries like the US and China, the UK, France, European countries, many of them are able to then, create that catalog that I was talking about earlier, which is a database of all of the space objects. Now, just a quick comparison between why I told you earlier that we can put these sensors in space and we can put these sensors on the ground, right? Now, from the ground, let's say this is your Indian landmass, and then you have that. India has, I mean, again, considering, wait, let me just go back here. Okay. So assume that, this is your Indian landmass, this is Sri Lanka, Kashmir, China. All right, excuse my bad diagram. But assume that this is an object that is there, right? If my sensors are only in India, then I can only track objects if it's passing maybe in this duration. If it's passing over India, then I can track it. But what about if the satellite is here, or it's never passing over India in the first place, or it's passing over India one day and I don't have enough sensors to even track it? That is the primary limitation of ground-based systems, right? They're geographically locked, whereas space-based systems are not geographically locked. As you can see here in this particular image, right? A space-based system is able to constantly orbit around the planet and increase what's known as coverage as well as revisit rate. Now, coverage and revisit rate are defined as, and let me just define coverage first. Coverage is the total number of objects from the existing list of objects that you can track. Say, for example, the total catalog of objects has around 10,000 objects today, right? With my sensor network, if I'm able to track 5,000 of those, that means my coverage is 50%. If I can track 7,000 or 8,000 of those, then it's 70 to 80%, right? Revisit rate then is defined as how many times can I image or gather data about that object per day. If I can do it once, it is 1, and so on and so forth. If it's multiple times, then the revisit rate increases. So the biggest difference is that for LEO objects, let's say if this is the planet over here, the Earth is constantly rotating, which means that the 16 times a day which the LEO object is passing over the Earth, maybe 2 times it will pass over India, right, at a given moment in time. It's unlike a GEO object which is constantly locked towards the Indian landmass or this particular spot. The LEO satellite will constantly be moving like this as the Earth rotates, right? So at one given moment in the day, it might be here, then it might be here, then it might be here. And the reason it's these curved lines is because it's going up and down and the Earth is constantly rotating. So if I have sensors only in India, then I can only detect it when it's moving over India. But in space, the number of passes, the number of times that the objects intersect, the number of imaging opportunities that are there, drastically increase both the coverage and the revisit rate. So the way you make your catalog better is you cover the most amount of objects and then you cover them more frequently. I'll tell you why this frequency is important as well. Now, Again, going back to my bad diagrams, they're actually good though. Um, if you're able to, let's say, image the object and then determine its orbit around the planet, right? You'll know that okay, it's going to be orbiting the Earth like this, right? And let's say you capture it today on the 22nd of February. But space is not, I mean, even though space is a vacuum, there are multiple factors affecting the orbit of a satellite, right? Earth's gravity is affecting it, which means that, let's say if this is the horizon and this is, a satellite that's passing over the Earth, it's not going to remain in this orbit forever, right? Especially in low Earth orbit, the Earth's gravity is constantly affecting it, right? There are solar particles that are affecting the motion of a satellite in its orbit as well. It's slow. So what happens is slowly, it will come down like this. So what satellite operators need to do is they need to burn some fuel to make it come back up into this propulsion orbit. This difference is what is this error difference that you see over here, right? Now, another example I'll give you, right? The satellite is orbiting, but suddenly it decides to maneuver into something like, this kind of orbit. You see this difference over here? Or rather, if we only capture the trajectory or image the object once every week, and as just assume that हाँ ये object जो है यही orbit में रहने वाला है, right? We will not be able to understand the fact that it has maneuvered in the first place. So that makes it important that we increase this revisit rate or imaging opportunities that exist, so that you're able to give the most accurate information about what the satellite's orbit is, and also detect any changes in its orbit. And changes in a satellite's orbit, as we discussed earlier in the case of Sindur, has a lot of real world implications in terms of the intelligence that we provide. So the different kinds of SSA tracking that can be done is this. You need, for basic SSA, you need, let's say, a catalog, right? Once you have a catalog can be the raw information or the orbital trajectory information of a satellite, right? Now, if you want to understand its behavior in quite a lot of detail, if you want, let's say, like a multi-pixel image like this. So let me just come back here to this slide. Yeah. Now, all of these different kinds of sensing mechanisms are giving me different kinds of sensing data and different kinds of space situational awareness. This is telling me what the position of a satellite is, let's say, in its orbit. It's giving me all of the orbital details. This is telling me how big the object might be and where its solar panels are, what kind of payload it has, where it's going to be looking. That has different, implications for different stakeholders. Passive RF systems give you the RF fingerprint, so you can listen in on what the satellite is saying or what the birds are saying in the sky. So different kinds of intelligence can give you different kinds of use cases. Let's just skip through all of this. So at Digantara, we are building, sensors and systems, or space-based sensors, essentially, to track satellites in orbit. Right? If any of you have gone to a space conference, you'll see that a lot of companies build optical systems to track what's going on the Earth. So Google Maps uses satellite imagery to tell you, what different portions of the Earth looks like. But our cameras go into orbit and look at different satellites and track different satellite objects. And it's quite a difficult engineering problem as well, because you have indigenous optics that need to be manufactured, indigenous electronics that need to be manufactured. Now, the electronics are again split into two, where you have a semiconductor chip that is there, which is the camera chip that is converting the light that you gather into an image. And then you also have an FPGA board, which is an embedded hardware systems board that is controlling how the payload operates, right? So all of this has to work, perfectly in conjunction with each other for us to be able to get what we want. So Digantara is already Digantara as well. Now, just coming back to this slide. So what I wanted to show you essentially is that I wanted to tell you guys as well, people who are aspiring to be in the space and are interested in space, etc., 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 is that 3 years ago or 3.5 years ago, I was also in your position, attending lectures like this, not knowing whether I had a future in the space industry in this country, right? Now, Kamini here has been to multiple conferences as well, and she'll be able to tell you guys that the industry is growing quite large today, but it's still at a very early stage, right? So at Digantara, the kind of teams that we need and the people that we need are not just people who can build hardware systems. We need people who have a background in astrodynamics. We need people who have a background in optical systems, electronics. Ops and legal guys. Running a company takes a lot of paperwork, sales and business development. So for all of these roles at the moment, we are, offering internships to people. And if you guys are interested in opportunities at Digantara, you'll be able to kind of reach out to Kamini and the staff here at DTU, and they'll be able to help you with those details, right? So Digantara is, India's only SSA company right now, and we have a combination of, ground-based sensors as well as space-based sensors to track objects. We're building these algorithms in-house as well to process the gathered data, and then we're tending or providing our solutions to a whole host of customer sets. That could be in civilian sectors, to ISRO and NASA, to other space companies and space operators like SpaceX, and to the Indian defense and defense companies or defense agencies outside of India as well. So I would have loved to give you a little bit more background as to what SSA means in a global context. But I'll be sharing some resources over with Kamini, and those who are interested can read these resources and understand what SSA means, and how you can get started with tracking satellites and developing your own programs. So that's about it from me. If you guys have any questions, then I'll be able to answer. And just before I wrap up, SSA maybe is 10 years old as a field. It's been around since about maybe 2015 or 2014. It's a very that's when the population of space objects started getting larger, and we needed somebody to track these objects. And it's technically hard. You need orbital mechanics, machine learning, sensor design, and real-time systems all working together. Every country needs it, right? Any country that's operating in space needs SSA. Anybody that operates a satellite needs SSA. And like I said, it's wide open for talent to join. There aren't enough people working on this particular problem yet. The question is that, it's not as if whether this matters. It does matter, as I've established in this particular session. The question is more to do with, do you want to help build it? And I'll leave that there. So thank you again, guys, for the opportunity to present what SSA is about. And I'll be here for any questions. And I think the DTU staff can take on from here.
Thank you so much, sir, for such an insightful session. Now, as mentioned earlier, it's time for a quick interactive quiz based on today's session. We have shared and pinned up Google form link in the chat box. The quiz consists of 5 multiple choice questions related to space situational awareness and key concepts discussed today. Please make sure you enter your correct name and email ID while submitting your responses. You will have 2 minutes to complete the quiz. The top 5 performers will be announced shortly and will receive a special shout out on our social media platforms. So let's make this interactive. Click the link and give it your best shot. All the best.
We will now open the floor for the questions. Participants may use the raise hand option to unmute and ask their questions, or type them in the chat box and we will read them out. We encourage questions related to SSA architecture, orbital debris management, ground-based versus space based tracking systems and emerging opportunities in space surveillance.
Okay, Neha, do you have any questions?
Yes, ma'am. Ma'am,
Okay, you
sir,
can
I
ask.
have recently started working on my dissertation in the area of space situational awareness. From your experience, what key research gaps or emerging themes should early stage researchers like me should focus on to build a meaningful contribution to SSA?
Yeah, it's a great question, and it's a very exciting journey that you're on, which is to build a dissertation on SSA. I would say that the performance. I mean, SSA algorithms is something that you can look into, right? Algorithms always need to improve. The computation times need to improve. We're also looking at different kinds of sensing modalities, right? Processing of SSA data from radars is very different from that of passive RF sensors or optical telescopes. So you can make a comparison between these different sensing modalities and understand which sensors are best for SSA. Then you could also look into something that's pretty intrinsic, which is data fusion. Because you're gathering data from different kinds of places, how do you fuse that data and make sure that it's not redundant and it's ultimately useful? So just to recap, it could be data fusion, it could be the sensors, and it could be in terms of the algorithms that you could sort of get started with, right? And that I would say are almost always research gaps available inside of the domain right now.
Thank you, sir. Sir, I have one more question if you
Sure.
allow.
Sure, of
Sir,
course.
how would you recommend defining a focused dissertation problem statement in such a broad, and evolving domain? So, how can I focus my research on a particular area?
Okay, so again, I will make it quite simple as well, giving an analogy to how do you come up with the research statement or research gap in the first place, right? Uh, in such a broad domain, you take one area which needs working on. Let's say, for instance, I showed you earlier that you can use images or telescope images to determine if a satellite is tumbling around in space, right? Now, you could focus on that one problem, the tumbling problem of satellites in space, and then understand, okay, what kind of algorithms are used to even process this data? There's different mathematical and statistical models that can be used to do this. So do a literature review on the different kinds of mathematical models that are used in prediction or processing of this information. Make a comparative study on those, and then maybe you can come up with a fusion algorithm that can combine two different statistical methods and come up with performance that's even better, right? So it's always about improving performance, improving data processing, improving data capture, and that's how I would kind of go about picking out maybe one niche problem inside of SSA or inside of the space industry, and then go about solving that.
Thank you, sir.
I think somebody in the chat had a question.
Okay, I would read that out for you.
Sure.
What do you think about the idea of putting data centers in space? Could they add to the space junk problem? And how would SSA handle that in future? Also, how can we make space data centers sustainable? It's a long question.
Okay.
Any questions on it?
Look, data centers in space. Let's just say that it will happen. It's been discussed, and it's something that is being talked about quite often. Elon has said it as well. So I'm not going to disagree with what he said. I'm just going to entertain the scenario that, okay, what if data centers are there in space? It's not going to be very different because of the fact that just like how we're able to track individualized objects, a data center also is an individualized object in space, right? You would be using the same algorithms to track where it is, whether it's going to be colliding with something else, etc., etc. And if, let's say, two data centers, or if there's a large data center constellation, or a number of data centers in orbit, then just like how we manage constellations today by ensuring that we have effective space mission operations and constellation management, and formation flying, etc., etc. The same kind of concepts and scenarios would be used to sort of manage the idea of of data centers in space, right? So in that sense, SSA is there's no need to like do anything differently towards data centers. Maybe keep an extra focus on them because they're important assets. But just like I told you, the same processing stack, gathering of data, processing of data, and then taking actions on that data can be used to entertain any object, not just data centers in space as well.
Yeah, I have one question.
Sure.
Okay, ask.
How can a master's How can a master's student enter the space situational awareness domain?
How can a master's student enter the space situational awareness domain? Okay, good question. Like I said, SSA requires different kinds of talent sets, right? You got to be good at you can be somebody who specializes in electronics because sensors have electronics in them, and we need people who can look at how to program hardware into behaving the way we need to behave, or way that it needs to behave. Optics is another thing because we're trying to develop indigenous optics. You can become if you're somebody who's interested in astrodynamics and orbital mechanics, you can maybe dive deeper into the orbit prediction and orbit modeling kind of side of things. If you're somebody who's into product and business, then you can make a business case and you can speak to customers about how the space data can help them. So there's multiple different pathways and multiple different routes for all kinds of master students, right from electronics to optics to people who are mastering doing their masters in computer science and building scalable software systems. At the end of the day, an aerospace company is a combination of not just people who are interested in space alone. Obviously, that passion must be there, but not all of us have done a degree in aerospace. I've done my undergrad in aeronautics, and unfortunately, 4 semesters of education is not something I can apply because airplanes use air to fly, and there's no air in space. So here I am still, functioning inside of the space industry. So you need different kinds of skill sets, right? It's not just that we only look at people from ISRO or only look at people from a space background. Any background is welcome to contribute to an aerospace field.
Thanks.
I have a question.
Sure.
What are the initiatives ISRO has taken towards the SSA capabilities, and what are the biggest limitations of SSA?
Okay. Let's try and speak about it from an India perspective, right? So ISRO, in fact, started taking a lot of different kinds of initiatives as early as 2021, 2022, where they've started a command and control center at the ISTRAC facility in Bangalore. Right? The ISTRAC facility is responsible for tracking and monitoring and C2 for all of ISRO space missions, and Project Netra is a part of one of their initiatives with which they aim to build sensors in India that can contribute to the tracking of space objects. Right. So ISRO has also released and continues to monitor all of the Indian assets in space. By this constant monitoring, they release a report every year, which is openly available and accessible on the state of our orbits. ISRO ensures and ISTRAC ensures that they reach out to commercial companies as well if let's say a commercial satellite is at risk. And Digantara and ISRO, and specifically ISTRAC inside of ISRO, are working closely together towards building an SSA future for the country. Now, coming towards its limitations, now there are no limitations to SSA as a concept, right? But there are certainly limitations or gaps in the SSA capability that we have as a country, right? It could be the fact that we rely on foreign data sets. It could be the fact that we don't have a lot of sensors or sensor networks to build an indigenous catalog, and that's what we're trying to do right now. And it could be the case that we need to train not just students and civilians, but also other stakeholders inside of the government on how SSA can be integrated into their current operational workflows, and become a use case for them. So I would say that we do have limitations in terms of SSA capabilities in comparison to other countries like the US, but we're not far behind, and we're certainly trying to catch up for sure.
Okay, thank you, sir.
Okay, we have a question in the chat box. I have done my undergrad in electronics and communication engineering and have been working in data science background. What other skills would I be needing to enter the SSA domain?
Okay, so you've done ECE and you're currently doing data science. Okay, so data science for us is more of a post-processing skill set, right? Let's say you, as I mentioned earlier, you gather all of the data into, let's say, a large catalog, and then you have to sift through that particular catalog, and then come up with AI/ML use cases or AI/ML algorithms and software to generate use cases for this data. So I would say machine learning is something that you should really get into. Heuristics is something that you should get into, and let's say understanding synergies between numerical, statistical, and ML-based algorithms is something that would be quite valuable to you if you're continuing down that data science path, right? But if you want to revert back to electronics, which is the more appealing field in my opinion anyway, I would say registry transfer language, RTL, is something that you should get quite comfortable with. Assembly, not a lot of students today learn assembly. They're all into C++ and Python, but assembly is something that you can get into as well, because when you're interfacing with hardware systems, it's difficult, or you can improve the performance of the control of these systems through, let's say, languages that interface with hardware better, right? Especially since this is operating in space, and if a server fails on the ground, then it's okay, like you can have a backup and things like that. But if something fails in space, it's quite difficult for us to get that started back up. So I would say learning hardware interface languages, learning about electronic systems that are used in satellites and payloads, like FPGA chips, like microprocessors, like CPUs, and the architecture of these kinds of things is quite important. And I'd like to tell you that there's a big talent gap in the world. I'm not even saying in the country today when it comes to people who are into hardware. Everybody wants to join, like everybody wants to learn C++ and Python and scale software systems, but I'm telling you guys, this is where the real hardware work is at. So yeah.
So anybody has any other question? Okay, so I have many questions. Your session was very insightful and very informative. So I wasn't expecting this from a company person, because I thought they hide things. Okay, but it was very informative, and we thank you a lot for that.
Okay.
So my background is basically in geospatial and geology, so I don't know much about SSA, but I got a few questions out of my curiosity, so I would be asking them. So, first is which sensor do you use to visualize artificial space objects? Like we understand electromagnetic spectrum. So, which part of spectrum do you utilize to visualize those objects? First
Okay.
question is this.
All right. So most telescope systems today operate in the visible and near infrared regime, right? It's just like the sun. The sunlight is hitting the satellite, and reflected light is bouncing off of the satellite and entering into our systems. I mean, the same principle is used to track satellites. So, that's one of the regimes in which we use the VNIR regime. Yeah.
I also saw some radar word in your PPT. So, do you also use radar, radio
Yeah,
waves?
yeah. We do use radio waves as well. Operating at very high frequency as well, because these are very sensitive objects and that sort of thing. So we use radar systems. We use passive RF systems as well. To kind of pick up object data in the S and X band. So there's different kinds of modalities that we can use to track objects and visualize these objects, so to speak, because data from these objects is then first captured, and then we can use algorithms to kind of visualize. I mean, earlier I showed you all small dots around the Earth, representing each individual satellite. That was all visualized using data that we've collected with these sensors.
Okay. Next question is how do you differentiate artificial and natural space objects?
Good question. How do we differentiate artificial and natural space objects? Okay, so the easiest, most common sense answer would be size, right? And the way that an object is particularly behaving, or the kind of orbit it is in, right? So, for instance, just purely based from based on an SSA kind of perspective, a satellite orbiting the planet is going to be very, very different from a comet orbiting the sun, right? So their orbital parameters and their trajectory is going to be very, very different. That's one. Second, using photometric analysis as well, you'll be able to tell what the orientation of a particular object is, or the size of a particular object using certain specific systems. Based on these kinds of data points as well, we'll be able to differentiate between artificial and natural space objects. Now, natural space objects, I assume you're alluding to, are comets, meteoroids, meteors, these kinds of things, right? A very interesting scenario is if an object is re-entering into the planet, is it a satellite or is it a meteor? I mean, it's just burning in the sky, right? So the way we're able to tell that is, again, it's all mitigated using SSA, or premeditated using SSA, where suddenly there's a gap in, I knew that a satellite was meant to be in its orbit, but suddenly it's re-entering. So what happened? So that's why, to differentiate effectively, we need to constantly monitor these objects as well. So yeah, that's how you can differentiate between the two, I suppose.
Okay, so this next question is like, it's a journal question. It's not only from you.
Sure.
For you, who is accountable if any artificial space debris falls on a city or a town?
Good question. It is, I mean, according to the conventions and liability rules laid out by UNUSA and COPUOS, these are UN conventions, it is the country that is liable for, if a particular object re-enters into and crashes into like a city. It's not the company, it's a country. So the nation's entire space program needs to be on high alert if, let's say, the scenario is happening, because the risk escalation moves from just, let's say, a company level kind of or organization level events to a national event, because now lives are at risk, right? So in that situation, the ultimate liability starts with the country's space program, especially if it's an international incident. So let's say if a US satellite comes in and it crashes, hypothetical scenario, I'm not saying that's actually going to happen. If it comes and crashes near our landmass or around our oceans, something has landed into Australia as well, then that particular company's government is answerable first and foremost, because these discussions happen on a international level and not, let's say, a company to company or company to government kind of level.
Okay, can if a particular objects fall on a city, can we identify who is the owner
Yeah.
of that object?
Yeah, we can.
Okay.
We can. That's pretty. That's one of the things that SSA contributes to, which is identification and tagging or naming of objects that are in orbit. So we identify and then we give a name tag to each and every single thing. So if there's a change in its behavior, like for example, it's re-entering, then we're able to identify, okay, who is the owner of that particular object? What is its country of origin? What constellation does it belong to? Is it a debris? Is it an active satellite? Anything like that.
Yeah, I don't know if you remember last year in Delhi, we saw few Chinese rockets part in the sky. The video was very viral. So, are you aware of that?
A few Chinese, those are not rockets. I don't think those were rockets. I think that was the Chinese space station Tiangong being constructed in orbit. I think it was that. I'm not sure if that's what you're referring to, but what's your question about it?
We saw something in sky from our buildings. It was like
Okay.
falling meteors, and then people said it is some Chinese rocket part falling, burning in the sky.
Right.
It happened last year.
Oh yeah, I mean,
It-
yeah, it could have been because recently as well, if a satellite or if a rocket body passes to a high enough altitude and then it's not able to make it and it comes crashing back into the Earth, then it breaks up in orbit and you'll see different kinds of streaks that are coming down. So that is a possible event as well. Yeah. I think somebody
Okay,
had a
my
question in the
next
chat.
questions.
Yeah, go on, go on.
Oh, okay. Okay, then let me just finish. I
Sure.
have few more. So, can you or or an organization like yours predict if any space object is going to strike Earth, if it were to strike today or in a week, like that?
Yeah, we can. So because I told you that we are monitoring the orbital path or trajectory of these particular objects on a daily basis, right? We will understand and know if there are slight deviations to its, orbital behavior or its orbital path. And if, let's say, it is to kind of, collide with the planet or re-enter into the Earth's atmosphere, there are indications and warnings that can be provided a week in advance to ensure that we're able to predict where on the planet it is going to re-enter into, and what is its landing zone going to be. So yeah, we can do that. And in fact, I would say that we've done this numerous times with numerous space agencies. One example being the Australian Space Agency that we're helping out with respect to re-entry mechanisms.
That is great. So this is a question from a geologist. That have you seen some changes in satellite orbit due to changes in Earth interior or ocean or air? Like the satellite has moved from its path due to some Earth activity.
Okay. Atmospheric activity, yes. Earth activity, no.
Yeah.
Right. So atmospheric, let me tell you like scenarios in which this could happen. Now, one of the more I wouldn't like to call it unpopular, but like less talked about, areas of aerospace is space weather, right? Space weather essentially is the monitoring of everything that is associated with our sun, right? Now the sun releases a lot of coronal mass injections. There are solar flares. There are solar particles crashing into the Earth's atmosphere, and that is witnessed by all of us as the aurora borealis that we see in the poles, right? Now that has a real effect in the particles that are kind of present in the Earth's atmosphere during such an event, right? And what happens is that these particles, they can interact with satellites as well and affect them, right? Let's say these are proton flux particles that could do that, or rogue particles that could interact with satellites, and if the satellites are not properly protected by radiation in radiation belts, then that could be a problem. But the biggest change that we're able to see is during such events, or generally speaking as well, satellites experience drag. Right now, some of you might be aware that aeroplanes experience drag because of the fact that we have an atmosphere and there are particles that are constantly forcing resistance onto an aircraft. There are also particles in the atmosphere, in VLEO orbit, like 350 kilometers to around 400 kilometers, etc., that are causing drag on satellites. And especially during solar events or space weather events, this could get highly intense, where the atmospheric density of these particles could increase, and this affects the satellite's orbit, right? And if the satellite's not burning enough fuel, then it could come crashing. In 2022, with the Gannon storm. The Gannon storm was one of the strongest storms or solar storms that we've seen in a while. And 33 Starlink satellites could not reach their orbital trajectories, and they came back crashing down into the planet because of high drag levels. So I wouldn't really say it's a geology thing, but it's more of, let's say, an earth sciences thing. That way.
Okay, that was very interesting. Thank you so much for answering all my questions. Let's
Sure.
take the last question we have here. How can your organization help geospatial students gain internships and build careers in SSA and related fields?
Okay, so good question. Like I said, geospatial students in this case, you guys have certain kinds of skill sets, okay? You guys have skill sets in image processing, right? You guys know how to process images and imagery. Those skill sets can be translated into, or for processing imagery that we collect, which is not, essentially it's, again, feature segmentation and distinguishing of all of these kinds of things. So just like how you guys are distinguishing features on a geospatial image, you can also use those very same algorithms to segregate features and process images that of satellites or of debris or something like that, right? So the principle is the same. It's just the image is kind of different. So image processing is something your skills can translate there. So if you guys have really good image processing skills, or you guys are into that domain, then yes, it could translate into an internship with Digantara, or organizations like Digantara. And that is how we can contribute to SSA as well. Additionally, if you have a keen understanding or a very good understanding of how Earth observation satellites work, then maybe you can come and help us model their behavior, model how their sensors work and how it translates to an image on the ground. And that way you can, contribute to our astrodynamics teams and in that respect. So there's multiple ways in which you can do it. You just gotta identify, how your core skill sets, maybe not your geospatial skill sets as such, but your core underlying fundamental skill sets can translate to, what it is that we do here or in SSA for that matter.
Okay, Vishal Singh Chauhan, do you want to ask something? You have raised
Yes,
your
ma'am.
hand. Okay, ask, please.
Hi there.
Right?
How are you?
All good, man.
Thank you for this very useful session. My name is Vishal, and I am currently working with Ministry of Defense right now.
Oh, lovely.
So I have sorry.
Oh, lovely. Yeah, go ahead, please.
So it's not related to SSA. It's a general question. is there any website or place from where I can get the sensor data of all the 15,000 active satellites?
Yeah, you can get open source data as well. And I'll be sharing these details with Kamini, right? And maybe she can pass them on to you. Is that okay, Kamini?
Okay, if it's okay with you, then I'm
Yeah,
also
it's
okay.
yeah, it's
Okay,
all right. It's all right with me. Vishal, any other questions?
Yeah, because I'm working on this application right now for Indian Navy right now.
Okay.
So I want to add the swath angle for the sensor so that I can track the area within the swath.
Okay.
So I need the sensor details of all the types of sensor right now.
Okay, so that information is unfortunately not available, right? I mean, that's where I get into like advanced SSA mechanics or advanced SSA, and that kind of those kind of services are not really available open source online. You would have to approach companies like us
Exactly.
who are you would have to approach companies like us who have been tracking these objects for a really long time and modeling these satellites for a really long time to be able to then achieve the use case that you want to achieve. Open
Right.
source, you'll only be able to get positional information. You won't be able to get the kind of payload information about
Exactly.
what.
I'm not getting that.
Yeah, so it's not really possible to get that open source. You'll have to do a lot of digging, and yeah, if you'd like to connect for this particular use case, you can just approach the DTU team, and they'll be able to pass on my details over to you.
Yeah, sure. I would like to invite you to my office one day.
Okay, awesome. Sounds good.
Kamini, will I be able to get his email address?
of course. I think Zaid, you can put your email in this message box. Okay.
I would.
If you
In
want.
fact, I'd want for you to kind of send it specifically to people who are interested. That way, I don't get spammed with unnecessary requests.
That's totally
Okay,
understandable.
I will share his email to you, Vishal.
Yeah.
Okay, Neha, please read vote of thanks. And Zaid, we have a message for you from Aryan Gihlawat. Please read
I
it from
haven't
the
completed yet,
box.
Kamini.
Okay, okay, go on, Vishal. Then.
Zed, can you then suggest me what other thing I can do if I'm not getting the payload data? So
I think
can you
Vishal,
just-
you can connect to him personally on his email because this session is about to end. Okay,
Okay, okay. Sorry,
is it okay for
my
you?
bad. It's okay.
It's okay. It's okay. Okay, Neha, go on. Neha, we can't hear you.
Sorry, ma'am. I forgot to unmute myself. So firstly, I'd like to announce the quiz winners. Thank you so much for the enthusiastic participation, everyone. It is truly encouraging to see such strong engagement and thoughtful responses. I will now announce the top 5 performers of today's quiz. Congratulations to Athar from BD Convent, Sakshi from DTU, Vishal Singh Chauhan from WESEE, Abhishek Dongre from WESEE, and Nana from IIT Kanpur. Let's give them a big round of applause. You will also be receiving a special shout out on our social media platforms. Once again, congratulations to all the winners and thank you to everyone who participated. As we conclude the final technical session of Geospace Tech Fest 2026, it truly feels like we are not ending a series but building a momentum towards something even bigger. Over the past sessions, we have explored careers, artificial intelligence, automation, and now space situational awareness. Your participation, questions, and engagement have made this journey incredibly meaningful. On behalf of Antriksh, the Geospatial Society of DTU, I would like to express our sincere gratitude to our respected HOD, Dr. K.C. Tiwari sir, for his continuous guidance, encouragement, and unwavering support. We also acknowledge the support of the Honorable Vice Chancellor, Dean Students Welfare, Dean PG, Dean UG, all deans, heads of departments, faculty members, the registrar, and the administrative heads of the university. A special and heartfelt thank you to Mr. Mohammed Zayed sir for sharing his valuable insights and helping us understand the importance of space situational awareness in ensuring sustainable space operations. I would also like to sincerely appreciate the dedicated efforts of the Antriksh Organizing Committee and volunteers whose hard work behind the scenes ensured the smooth execution of every session throughout the series. And finally, thank you to all our participants. Your enthusiasm and consistent engagement have truly made Geospace Tech Fest 2026 impactful. And now, I would like Hitesh to share his screen and share the posters. We are extremely excited to officially invite all of you to the main Geospace Tech Fest 2026 happening on 27th and 28th February. The fest will feature multiple engaging and competitive events, including technical competitions, case study challenges, quiz competitions, innovation and problem solving events, and exciting space themed activities. We strongly encourage all of you to participate and showcase your skills. The registration link will be shared in the chat right now. Please make sure you register at the earliest. We also request everyone to regularly follow our official social media platforms as we will be releasing detailed guidelines, event rules, problem statements, competition updates, and important announcements. So please stay tuned and keep checking our socials for updates. We truly look forward to see high energy participation and enthusiastic engagement from all of you during the main fest. Let us carry forward the curiosity, learning, and momentum built through these technical sessions into the grand event on 27th and 28th. Thank you everyone for being the part of the Geospace Tech Fest 2026. See you all at the main fest.
Okay, bye bye all. Thank you so much for joining.
Thank you, ma'am. Thank you, sir.
Thanks a lot, guys. Speak to you all soon.
Thank you.